Hey everybody on Zoom. Sorry for the late start here. I was having trouble getting logged into the system. For those of you in class, by the way, I misplaced my QR codes, so fill out the attendance form when you have a moment. Go to the link in Canvas or whatever, or have already bookmarked it. Let me share my screen with you all. Let me give you all the attendance form just in case you didn't already get there. So the plan for today is just to address questions from either the practice midterm or other places. I have a few ideas as well, but a couple people have already asked for a couple things, so we'll start there. If anyone on Zoom has specific questions from the Dell's midterm 2 practice questions, feel free to put them in the chat. Speaking of the chat, there we go. Here's the attendance form. All right, let's get going finally at 9:07. All right. So the first couple were question 3 and question 16 from his practice. So here's question 3. It's determine, not determined, the equilibria. I'll get this to be perfect. For dn dt equal to 5n minus n squared, and determine stability. And then says the parts A and B determine stability using the graphical approach, which is the phase plot, and the analytical approach, which is the stability criteria, where you just find the derivative of the thing and do the thing. And I'm gonna, before we even start with this question, I'm gonna ask, is this differential equation pure time, autonomous, or non-autonomous? Definitely autonomous, because our derivative only depends on the top thing, not the bottom thing. So dn dt only depends on n, that means it's autonomous. If it only depended on t, it would be pure time. And if there were both n's and t's over there, it would be non-autonomous. Cool. All right, so to determine the equilibria, we take the derivative that we've already been given, dn dt or dx dt or dy dx or whatever the derivative is, and set what it's equal to 0. So we're going to set 5n minus n squared equal to 0. And then we're going to factor. You never want to bring stuff to the other side. You just want to keep 0 on that side. And we're going to factor as n times 5 minus n. And we're going to end up getting n equal to 0 and n equal to 5. And those are equilibria. For those of you in the chat, I see all your questions, and we'll definitely get to all those in the order I see them. So for part A, we're asked to determine stability using the graphical approach. So when you're doing the graphical approach, you're drawing the graph of this thing. You're essentially thinking of this as g of n equal to 5n minus n squared. Or if it's easier for you to think of it, you can think of it, but don't write it, as f of x equal to 5x minus x squared. We already have the intercepts. There's 0 and 5. I would definitely encourage you to label your axes, by the way. The horizontal axis is n. The vertical axis is your dn dt. My intercepts are n equal to 0 and n equal to 5. This is a parabola. Is it upward or downward opening? Definitely down because of the negative n squared. Or if you don't like to think of it that way, you can pick a point between 0 and 5, like 1, and plug it in and get 5 minus 1, which is 4, which is positive. So between 0 and 5, it's got to be positive. It's doing something like this. And people do this maybe slightly different ways. The way I always think about it is, if I'm in here between 0 and 5, dn dt, we just said, was positive, which means n is increasing or decreasing? Increasing. I like to draw these little arrows that means n is getting bigger. Over here to the right of 5, since dn dt is negative, n is decreasing. And similarly here to the left of 0, since dn dt is negative, n is decreasing. Oh, sorry, you can't really see that very well, sorry. And then I look at each of the equilibrium. I think, okay, for the equilibrium of 5, we're getting pushed in towards 5. which means we're stable. For the equilibrium of 0, we're getting pushed away from 0, which means we're unstable. I think that's enough work to say, great, n equals 5 is stable, n equals 0 is unstable. That's how I would do the first part, doing using the graphical method. So if the arrows point towards your equilibrium, it's stable. If the arrows point away from equilibrium, it's unstable. And I think that's all you really have to say. Using the other method, what's it called? The analytic approach. So we're going to take our dn dt, which is equal to 5n minus n squared. And I personally like to call that g of n. That's the typical kind of thing we do. So we're going to say, let's call it g of n equal to 5n minus n squared. We're going to take the derivative of that. So we're going to find g prime of n, which is just 5 minus 2n. And then we're going to plug in each of our equilibria. So first, g prime of 0 is 5 minus 0, which I don't really care that it's 5. I just care that it's positive. If your derivative if your derivative after equilibrium is positive, that means we are unstable. Really for the same reason as the graphical method. If you look back at that point there where we can see it's unstable because you're pushing away from it either way, the slope of the tangent line there is certainly positive. So the derivative of this graph being positive means the equilibrium is unstable. And similarly, if we plug in the other equilibrium, 5, g prime of 5 is going to be 5 minus 2 times 5, which is negative 5. Again, I don't really care about the value. I just care that it's negative. That means we are stable. And I really should say unstable at n equals 0, stable at n equals 5. That's pretty much it. Oh, except I'm going to ask another question. So any questions about this before I add on another question, which I think is a great question personally?
I have a question. So wait,
Yeah,
how did
go
you
ahead.
determine a plug-in 5?
Say that one more time.
How did you determine a plug-in 5 for part 2?
Because well, I'm going to answer a bigger question. How did I determine to plug in 0 and 5? I determined those because those were the equilibria we found from the first part. And we found those equilibria by setting the original differential equation equal to 0 and solving for n. Because again, when you're finding equilibria, you're finding where things aren't changing. And if things aren't changing, that means the derivative has to be 0. Cool. So now here's what I think is an excellent question. Let's say that we're given the initial condition. So let's say we're given that n of 0 is equal to 7. And then I'm going to ask something. What is the limit as t approaches infinity of n of t? I'll address that question in a second, Crystal. We don't know what n of t is. And we're not really expected, at least on this exam, to solve differential equations. And we don't have to. But they're saying, okay, well, if you start at, I don't even have the graph, right? This is not the graph of n versus t. This is the graph of the derivative versus n. But here's the idea. What's happening here is we're saying, well, I know that in the beginning, when time equals 0, the value of n is 7. So that means I'm starting right there. And if you start right there, which way do you get pushed? To the left, which is towards 5. And you don't get pushed further than that because if you go further than 5, you get pushed back towards 5. So we can say that the limit as t approaches infinity of n of t, if we're starting at the 7 when time is 0, that must be 5. You could write a few more words if you want to. You can say, because when n equals 7, dn dt is negative, and we decrease towards the stable equilibrium that is 5. I like this question personally, as you might have gathered. I think it's makes you really think about what's going on here. And certainly other instructors have asked questions like this on exams in the past. Somebody asked, isn't the original equation already the derivative though? And yes, so I would say the original equation, dn dt equal to 5n minus n squared, is your original differential equation. And we're saying the derivative of n with respect to time is equal to this. But then we're kind of viewing this graph as a function of n. So we're taking the derivative of that function of n with respect to n to do this criteria test the second way. That's what's happening there. Yeah. All right. Moving on to number 16. And again, I'm just going in the order people asked them. So yeah, 16 is a good one. Yeah. I mean, they're all good questions in one way or another. And that's probably not entirely true, but whatever. All right, so number 16, here's the setup. Suppose a population grows according to the logistic equation, but is subject to a constant per capita harvest rate of H. If N of T is the population size at time T, the population dynamics are given by I feel like there's a letter missing in this. So I'll point out at least the one I just printed out says the equation is n dt, and I really think that should be a dn dt, right? The derivative of n with respect to t, not just n over dt is really is nonsensical. So I'm pretty confident that should say dn dt is equal to r times 1 minus n over k times n minus h times n. And then it says different values of H result in different equilibrium population sizes. If H is large enough, we might expect extinction. Okay, great. So part A, suppose R equals 2 and K equals 1,000. Find the equilibria. Okay. Again, when we find equilibria, we're gonna. So we could even do this without plugging in R equals 2 and K equals 1,000, but we should do it that way because it's going to be less terrible. So we plug this in, we're going to get 2 times 1 minus n over 1,000 times n minus h times n, and we're going to set that equal to what? 0. And I'm always going to look to factor as much as possible. And I'm going to notice that from both this thing and this thing that are subtracted together, I can factor out an n. So if I factor out an n, I'm left with 2 times 1 minus n over 1,000 minus h. It's not always going to be true, but it's often going to be true that n equal to 0 is going to be an equilibrium, because if your population has size 0, it can't grow. That's not always the case, but it is often the case. So then I'm either going to get n equal to 0, great, or this other quantity equal to 0. So let's do the algebra. So we got 2 times 1 minus n over 1,000 minus h equal to 0. And I'm trying to solve for n. I'm going to distribute the 2. You get 2 minus 2n over 1,000 is n over 500 minus h equal to 0. I'm going to isolate the n over 500. You get 2 minus h equals n over 500. And then multiply both sides by 500 to get 500 times 2 minus 500h equal to n. There's my other equilibrium. And good, the question says find the equilibrium. Hint, one will be a function of h. So I'm feeling pretty good about my answers. One of them is 0 and one of them depends on h. Moving right along. Part B, gosh, I really have this. Sorry, it's terrible. For part B, the question says, for the non-zero equilibrium, what is the critical value of h greater than which the population will go extinct? Okay, interesting. So, for what value of h, what is the critical value of h? For what critical value of h? Sorry, I feel like I'm writing this terribly. What is the critical value of h greater than which, I don't love the way this is phrased, greater than which the population will go extinct? Okay. So h is the harvest rate, meaning we're essentially taking away some amount of the population every so often. I don't really think about this a whole lot. So I don't actually have a good idea about this. To be perfectly honest, like I have not thought about this really a lot, but I'm guessing we're saying, I don't really know. I really, really don't know. Like, do you guys have any intuition? Has he talked about this? I have an idea. My guess would be h equal to 2. I don't actually know that's the right answer. I'm just making an educated guess here because I'm seeing that if h is equal to 2, then this end value is going to end up being 0. But I don't actually know. I'm going to go look at the solutions. Right, the solutions? Seems reasonable. Sorry, I know. I mean, so here's what I actually think. I would imagine it to be a value that when you pick that value, your dn dt would end up being negative no matter what you did. That's what I'm kind of thinking. Let's do that. Let's actually before I look at the answers. So let's see here. So our dn dt is equal to this whole thing again, this n times 2 times 1 minus n over 1,000 minus h. And if, oh yeah, totally. So if I simplify this a little bit, specifically the insides here, this is n times 2 minus 2n over 1,000 is n over 500 minus h. And if h is 2 or bigger than 2, so if h is bigger than or equal to 2, then 2 minus h is for sure going to be negative. So then that's going to equal n times 2 minus h minus n over 500. And then if h is bigger than or equal to 2, 2 minus h is for sure negative, minus n over 500 is also negative, and the whole thing's going to be negative. And if that's
Why do you
negative,
want the
hold on, just one sec. If that's negative, then our rate of growth, or growth rate is negative, which means our population is going to be decreasing no matter what happens and eventually die out. Go ahead.
where in the question did it say that it will decrease? I'm just trying to like
Well, it doesn't
figure
say that. So what the
Yeah.
question says is, what is the value of h where the population will go extinct? Well, if the population is going to go extinct, the growth rate has to be
0.
not 0, actually.
Oh, negative.
So if the growth rate is right, if the growth rate is 0, the population is just chilling, right? In fact, those are equilibrium points. When the growth rate is 0, that means the derivative is 0, which means you find the equilibrium. So this population, well, in the previous problem, like the population could have been 5 and just sat there forever and ever and ever and been fine with the growth rate of 0. But if your growth rate's negative, that means your population is decreasing. And if it keeps being negative, you're eventually going to decrease until you get to 0. So that's how you should interpret that. If you're asked about what values you need for something to go extinct, you have to find the thing that makes your dn dt, your growth rate, always negative. Yeah, okay. And there's a part C as well. Yeah. Determine the values of h that make the non-zero equilibrium in part A locally stable. Assume that h does not equal 2. So there's a good lesson in reading ahead. If I had read ahead, I wouldn't have had to think so hard about what h was going to be. I would have been a really good guess that h should have been 2 if I'd read that question ahead, because they're kind of telling you maybe what the answer would have been. So part C, values of h, little h, that make our previous equilibrium, which I'll remind myself was n equal to 1,000 minus 500 times h, to make that locally stable. I really don't want to graph this, so I'm going to use the other stability criteria, which is taking the derivative of this thing with respect to n, and then seeing what values make it negative so we get stability. Okay, so looking at this, this is not the version I want to take the derivative of. I don't want to have to use the product rule if I can help it. So I'm actually going to go back to the original version and say that my dn dt with my values plugged in is 2 times 1 minus n over 1,000 times n minus 8 times n. And I'm going to multiply this out before I do anything else. So multiplying this out, I really have 2n times 1 minus 2n times n over 1,000 is n squared over 500 minus h times n. That's my g of n. That's the thing I'm going to take the derivative of to then plug into. So my g prime of n is going to be 2 minus 2n over 500 minus h. And then we're going to test the stability of this by plugging it in, right? That's how we usually test the stability of our equilibrium. We plug it into this derivative, and then we hope it's negative, or we're going to find the criteria to make it negative. So of course I've run out of room here. So we're going to do g prime of 1,000 minus 500h, because that 1,000 minus 500h is our equilibrium, our non-zero equilibrium. And if we plug that in, we're going to get 2 minus 2 times 1,000 minus 500h over 500 minus h. We should clearly simplify this expression. We can factor out a 500 from the top part and get 2 minus 2 times 500 times 2 minus h over 500 minus h. The 500s cancel. We end up with 2 minus 2 times 2 minus h, which is going to be 2 minus 4 plus 2h minus h, which is going to then be h minus 2. And if we want that to be, what do we want that to be? If we're trying to get stability, do we want this derivative to be positive or negative? Negative. So we want this to be negative, which means we want h to be less than 2. And I suppose, let me just double check one thing here. I think reading the problem, h kind of has to be positive. Like if your harvest rate is h, it wouldn't make sense to have a negative harvest rate. So I would say more specifically, h is between 0 and 2. You can probably get away with just saying that h is less than 2. Some questions here. Let's see. So I just paired 2 minus h together. So when you set it equal to 0, it will be 2. Yeah, kind of. I'm not exactly sure what that's asking. How do I know when to make it greater than sign equal to or not? Don't remember where I was doing that. Yeah, I'm not exactly sure. I think that's over here, but I'm not exactly sure why. That's what we're like, why I was saying that. Yeah. Oh, I think I was just saying, well, I guess if H had been 2. No, that seems fine. I don't know. I'm not exactly sure here, to be honest. You probably could have just as easily said H is greater than 2 and been fine. And then as far as the quotient rule thing, we don't need to use the quotient rule here. Take the derivative of n squared over 500, because if you're dividing by a constant, that's just like multiplying by a constant. So you can really think of that as 1 over 500 times n squared, and the derivative is 1 over 500 times 2n. So that's what's going on there. You could use the quotient rule, but shouldn't. Other questions about this? It's a challenging question. I think this question is hard. It's making you have to really think. And also, right, there's like this H thing in there that's just kind of sitting in there that we're not having a specific value for. So yeah. Someone else told me it should be less than 0. I didn't do it. But so the real answer is, when we're doing this process, right? So actually back to the first question, right? When I was trying to find whether these two equilibria were stable or unstable, one way was graphically, where I said, okay, this one's unstable because we're pushing away, this one's stable because we're pushing towards it. But then if I thought about this function as g of n, I'm noticing that at the unstable one, the derivative of g of n is positive. And the stable one, the derivative of g of n is negative. And so that's actually how I'm getting the criterion, saying, oh, I know that if I take the derivative of whatever dn dt is equal to, if my equilibrium point has a negative derivative, it's going to be stable. So I said, oh, I took my derivative, I plugged in my terrible equilibrium, I simplified it a whole bunch, and I said that I know to be stable, right, this being this derivative, this g prime of n, being less than 0, that's what's giving me stability. Whereas if your g prime of your equilibrium is bigger than 0, that's giving you instability or unstableness. That's how I knew to set it less than 0. Other questions?
If you were asked to find where the function is increasing or decreasing, how would you
Or the
go
what?
about that?
Sorry.
Sorry, where the function is increasing and decreasing? Like for a different function, maybe, like,
yeah.
would you go about it like taking the derivative or finding the critical points and then plugging it back into the original equation, not like taking the derivative and plugging it into the derivative like we did here?
If I was trying to find where the original function or the differential equation. Because the thing is, like, I don't know about none of this can be used to find whether the original function is positive or negative. We can talk about the derivative being positive or negative, but we can't really talk, and which will tell us if the function's increasing or decreasing, kind of like in the first question we did.
Okay.
We're not saying that H is unstable. We're saying that if H is less than 2, then our equilibrium is going to be stable. So what we're saying is n hat, we use a hat when we talk about equilibrium for whatever reason, n hat equal to 1000 minus 500h is stable if h is less than 2. And if h is big, it also, right, it would also be kind of weird if h is bigger than 2, because if h is bigger than 2, then your n would be negative, and the negative population is kind of strange to think about. Could I also set that 5n minus n squared equals 0 factor? Yeah, that's what we did in the beginning. We definitely, for the other problem, we set in factor. Yeah, you can use test points to test for stability. No, not, I mean, again, the way we're testing for stability is either the graphical method like we did, or the derivative method like we did after that. But you don't really want to use test points. You want to test the stability of the actual equilibrium. So those are the things you plug into the derivative to test for stability. Why couldn't H be negative? Because they talked about H being the harvest rate, and the harvest rate seems like it should be a thing that's positive. At least that's more my, I guess, more my opinion of what the actual physical meaning of it is. I suppose it's technically possible that h could be negative, but I don't think it's meant to be.
I have a quick question.
Sure.
Just to clarify, for part B, we're just trying to find what value of h makes the derivative d like negative, or they
Correct.
both rate negative.
Yes, we're trying to find the value of h that makes the derivative when you plug in your equilibrium negative. All right. Let me scroll back here. So the next question on deck, number 14, another fun word question. Oh, that one's not too bad. Oh yeah, this one's not too bad at all. Cool. 14. So here's what 14 says. 14 says verify that y equal to t cosine t minus t is a solution to t times dy dt equal to y plus t squared times sine of t, with y of pi equal to 0 as your initial condition. And as far as I can tell, that initial condition is completely useless in this problem. Just fine. But just be aware, sometimes you're given extraneous information that doesn't actually help you at all. So to verify something is a solution to a differential equation, we first should look at the differential equation. And in this differential equation, I see my original function y and its first derivative, dy dt. So I know I need to find the first derivative. If there had been a second derivative, I would also find that. So first step, I'm going to find dy dt. So great, I'm going to take my y, which is equal to t times cosine t minus t, and take the derivative of that. So I'm going to use the product rule for t times cosine t. I feel like I'm missing a sign here. No, I guess not. Okay. The derivative of t times cosine t is 1 times cosine t plus t times the derivative of cosine is negative sine of t. And the derivative of negative t is negative 1. So there's dy dt. And then I'm just going to look at each side of this equation and plug in whatever y or dy dt is equal to. So the left-hand side of my equation, which is t times dy dt, is equal to t times all of that. Cosine of t. I'm going to simplify this a little bit and write it as minus t times sine of t minus 1. I do feel like there's a mistake here. Whatever, we'll figure it out. So then, distributing the t, I get t times cosine of t minus t squared times sine of t, which is worrying, minus t. Okay. And then the other side says, or I should say, and then the right-hand side of this equation is y plus, that is a plus, right? I'm reading it right? Yeah. Y plus t squared times sine of t. And then I'm going to plug in what y is equal to and get t times cosine of t minus t plus t squared times sine of t. And then we ask, are they the same? And we notice here that they are not. Yeah. That's what I thought too. It's definitely not showing up in the one I just printed out. Okay. So there we go. So we can see here that it's not turning out. So we should have a negative t there, which means our derivative would have been negative 1 times cosine of t plus negative t times negative sine of t. And then our left-hand side would have been t times all that. So fixing this a little bit, it's a t times a negative cosine plus t times sine of t, still minus 1. We distribute the t, we get a negative t times cosine of t plus a t squared times sine of t minus a t. And then our y plus t squared sine of t should be negative t cosine t minus t plus t squared sine of t. And then we ask, are these the same? Let's see, negative t cosine t plus t squared sine of t minus t. Yep, those are the same. The right-hand side is equal to the left-hand side. And that's all we have to do. We just have to check and make sure that when you actually take whatever derivatives are in there and plug them into each side of the equation, both sides are in fact actually equal to each other. And we're done. Yeah.
So you always check both sides.
Well, yes, if there are things to plug into both sides. Like if this had been like the entire left-hand side was like y prime plus y double prime plus 2, and the right-hand side was like equal to 3x, then no, I'd really just work with the left-hand side and simplify it until it was equal to 3x. But in this case, there's a derivative to plug in here and a function to plug in there. But we're always plugging in whatever y and its derivative and the second derivative and whatever derivatives you have are equal to.
And then
Mhm.
for the initial condition, we just like
It is not helpful at all here. We do not need it. You could, no, there's absolutely no reason to talk about the initial condition. Interesting. Yeah, that's fine. Cosine, yeah. I mean, sure. Yeah, it's true, right? If you plug in pi for t, you will get y equal to 0, but that doesn't really tell us anything. Yeah, so you almost never need an initial condition when you're verifying a solution. So there's a couple of questions. So this was, no, this was a differential equation, right? So I will say this right here, this is a differential equation. What I'll say is we were not solving this differential equation. We were already given the solution. We were just asked to show that it in fact was a solution. And again, as far as I know, right, he sent a message saying, you're not responsible for solving any, you're not responsible for solving any differential equations, whether by separation of variables or by first order linear, which is what I would love to be talking about today, but we're not talking about it. So that none of the solving should be on this. That doesn't mean you shouldn't be able to set up a differential equation or analyze the equilibria or draw a phase plot, but you shouldn't have to solve any differential equations. Yeah.
the first one. Where's the negative one?
This negative one here, because the derivative of negative t is -1. This is non-autonomous. Good question. Yeah, this is non-autonomous. Because if you isolated dy dt by dividing both sides by t, you would have the dy dt dependent both on y and t, so it would be non-autonomous. All right. Question 4 is up next. Oh, this one's interesting. Yeah. So I imagine this one slightly differently than he did, but that's fine. So number 4 is not a differential equation. It's find the number find such that the line x equal to a, which is a vertical line, bisects, that's not the easiest for me to say, the area under the curve y equal to 1 over x squared on the interval from 1 to 4. So here's how I imagine doing this. We can talk about the other way, but I think my way might be better. Surprise, surprise, right? Me thinking my way is better. The thing I would do first is actually find the area under the curve. So the area that we're talking about, not that you have to draw, but looks like this. It's just going to be the integral from 1 to 4 of 1 over x squared, which is the integral from 1 to 4 of x to the -2. We anti-differentiate, we get x to the -1 over -1, 1 to 4. I really don't like leaving it like this. I would much rather write that as -1 over x from 1 to 4, and then plug in the 4, plug in the 1. You get -1/4 plus 1, which is 3/4. So that's how much area is under the curve. And now what we're looking for is we're looking for the number a, so that half of that area is on this side and half of it's on the other side. And half of 3/4 is 1/2 times 3/4, which is 3/8. So we're trying to find the number a so that the integral from 1 to a of 1 over x squared dx is equal to 3/8. Or if you prefer, you can say the integral from a to 4 of 1 over x squared is equal to 3/8. That would be equivalent to the statement here. So then if I do this integral, we already know what this integral is. The integral of 1 over x squared is once again negative 1 over x. So we're going to say that negative 1 over x evaluated from 1 to a has to equal 3 over 8. So then negative 1 over a minus negative 1 over 1 has to equal 3 over 8. Simplifying things, we have negative 1 over a plus 1 equals 3/8. Subtract 1 from both sides. 3/8 minus 8/8 is negative 5/8. Oh, that's an a, not an 8, sorry. Woo. Multiply both sides by negative 1, and then take the reciprocal of both sides. So 1 over a equals 5 over 8. So a over 1 equals 8 over 5. That's how I would do it. He did it a slightly different way in the solutions. He set it up by saying the integral from 1 to a is equal to the integral from a to 4, and then found them both and set them equal to each other and solve for a that way. To me, that seems more algebraically complex than doing it this way. This might feel like a little bit more work. I don't really think it is. So this is the way I would do a problem like this, and I think it's easier to do it this way.
So we get the 3/8 to just assume that it was just 1/2.
So one more time.
Like, so you know the area is 3/4, right? And so since they say bisect, you just assume that meant like split in half.
Right, yeah, exactly. Yeah, it says in the problem here, I think, right, it bisects the area, so splits it in half. Yeah. I would say I would maybe use the word split in half instead of bisects, but yeah. Yep, so that's not a problem. Let's see, up next is 9C and then 15. And then that's all the things people have asked for so far. So, oh gosh, 9C, okay. Ooh, we've done this one before. Not my favorite, but it's all right. It's 9C. Have we done this one before? I think we have. Sine of the natural log of x. I'm pretty sure we've done this one before. Okay, this one you can do 2 different ways. The way that seems the most sensible to me is to start with a u sub, and then it's going to be integration by parts. Since I know that starting with a u sub is going to lead me to integration by parts, I'm going to do my u sub with a different letter. I'm not going to use u. I'm going to use t. So we're going to let t equal the natural log of x for our u sub. So then if t equals natural log of x, my dt is not helpful. I don't have a 1 over x dx, but I know I'm supposed to do this u substitution first. So instead of going that direction, when you find that your d whatever is not helpful in your u substitution, that usually means it's helpful to take your u substitution and solve for x. So I'm going to take t equal to natural log of x and write that as e to the t equal to e to the natural log of x. And so just to answer the question for the previous one, we got 3/8 by multiplying our area of 3/4 by 1/2. 3/4 times 1/2 is 3/8. And then e to the natural log of x here is x. So then we have x equal to e to the t, and we're going to take the derivative of both sides to get a dx. The derivative of x is 1 times dx. The derivative of e to the t is e to the t times dt. So then we can replace our dx with e to the t times dt. And our sine of natural log of x will become sine of t. So this is going to become the integral of sine of t times e to the t dt. And then we're in one of these unfortunate situations, specifically e to the x times sine of x, or e to the x times cosine of x, where you have to do integration by parts twice. The same integral shows up again, you add it back over to the other side, and then divide by whatever the coefficient is, which will be 2 in this case. So that's what we're going to do here. It's kind of gross, but it's totally doable. So we're going to let u equal, this is, by the way, this is why I chose t, so that then I could use my u and my v like I like to when I do integration by parts. So my u is equal to sine of t My dv is e to the t dt. So that's a little small there. My du is cosine of t dt. And my v is just e to the t. This is going to end up equaling u times v. So e to the t times sine of t. Minus the integral of v du, which is e to the t times cosine of t dt. And we do it again. For this new integral here, we're going to let u equal the trig thing again. dv is the rest, which is e to the t times dt. My du is negative sine of t times dt. My v is e to the t. By the way, I was reminding someone the other day that for your trig functions, all of the co-functions have negative derivatives. So cosine, cotangent, cosecant, all have negative derivatives. Whereas the other three, sine, tangent, and secant, have positive derivatives. Reminder, I'm talking about the derivatives right now, not the antiderivatives, the derivatives. So just a reminder. So then here, we're going to get e to the t times sine of t minus, now we're going to do the uv minus vd, integral of vdu again. We get u times v, which is e to the t times cosine of t, minus the integral of v du, which is e to the t times negative sine of t dt. So now we're going to do the simplification. We're going to, and I think it's helpful to write out the integral we're starting with on the left. So we have the integral of sine of t e to the t dt is equal to e to the t sine of t minus e to the t cosine t. And it really better end up being a minus the integral again. Because if it was a plus, then they would just cancel out and that would be weird. But it is a minus because it's a minus, a minus, a minus. So it is minus the integral of e to the t sine of t dt. We add that to both sides. We run out of room on our paper. So we add this to both sides, plus the integral of e to the t sine of t, plus the integral of e to the t sine of t. Doesn't matter what order you multiply things in. E to the t times sine of t is the same as sine of t times e to the t. So then on the left-hand side, we have 2 times the integral of e to the t times sine of t dt equal to just that part right there, which is e to the t sine of t minus e to the t cosine of t. And then finally, well, not finally, then next we divide both sides by 2 and write that our integral of e to the t sine of t dt is equal to e to the t sine of t minus e to the t cosine of t divided by 2 plus c. But we're not done because remember we started off with x's, not t's. So then after we've done all this stuff, then we have to go back and say, oh, but wait, t was equal to the natural log of x. So our original integral, the integral of sine of natural log of x is equal to plug in natural log of x for every t and get e to the natural log of x times sine of natural log of x minus e to the natural log of x times cosine of natural log of x divided by 2 plus c. And then I really would feel bad leaving it this way. E to the natural log of x, we should really just rewrite that as x. So we should really do one more, like normally it'd be like, fine, don't simplify, but here, if you don't simplify, I don't want to say you're a bad person, but I wouldn't leave it unsimplified. X times sine of natural log of x minus x times cosine of natural log of x, all divided by 2 plus c. Gross. Kind of a lot. I mean, that doesn't mean Dedel wouldn't put it on. I feel like you can't ever caveat that, like, that's a hard question, but totally something probably Dedel could put on the exam. It feels like a lot though. To me, this one feels hard because you have to know to first do the U sub. Alternatively, just so that we won't do it, I'll just point out you can do this one, doing that and erase my parts twice process by just starting with letting be like, if you look at the integral of sine of natural log of x, you can do this immediately using erase my parts by letting u equal the entire sine of natural log of x and dv equaling dx. I don't think it's any easier this way because you still have to do it twice, end up with the same integral you started with, add it over to the other side, divide by 2. But if you weren't able to see the u sub with the back sub kind of thing, this is another way you could attempt to do it. Whew, all right, let's look at number 15 and then number 13. Okay. A population is, oh, sorry, I should write down the words. Number 15. For those, and by the way, for those of you that are in the not Nadel's class, I will also post these questions and their solutions on our class website just so you can see them as well. They might be helpful. They might not be helpful, but they're certainly worth looking at. 15. A population is modeled by the differential equation dn dt equal to 1.2 times n times 1 minus n over 4,200. Where n of t is the number of individuals at time t, which is typically what we talk about. For what, question A, for what values of n is n of t increasing? Or they say, is the population increasing? But that's just n of t. Okay, what's a better way to ask this question? Instead of asking for what values is the population increasing, I should say for what values is the derivative positive? That's all we're asking. Where is the derivative positive? Well, to find where the derivative is positive, it really makes sense to find where the derivative is 0. So let's find the equilibrium. Even though we haven't been asked to, it's usually a good idea to answer any kind of question about increasing or decreasing. So we're going to find the equilibria in the usual way by setting the derivative that we were already given, which is equal to 1.2 times n times 1 minus n over 4,200 equal to 0. And I think the equilibria are pretty easy to see here. One of them is definitely n equal to 0. What's the other one? Let's see, I need this factor to be 0. So I need 1 minus n over 4,200 to be 0, which means n over 4,200 has to be 1, which means n has to be, yeah, 4,200. And then I'm essentially going to make the phase plane. Even though we weren't asked to, it's really useful. So here's my n, here's my dn dt. My equilibrium is 0 and 4,200. And maybe this is what someone was asking about before. This is where I'm going to kind of just plug in values in between to see. So I pick a number bigger than 4,200, like a billion, and plug it in. 1.2 times a billion is positive. 1 minus a billion over 4,200 is still a pretty big number. 1 minus a pretty big number is a negative number. So it's a positive times a negative, so it's going to be negative over here. So that means our dn dt over here is negative like that, which means n is decreasing. Between 0 and 4,200, I'm going to pick 1. 1.2 times 1 is positive. 1 minus 1 over 4,200 is also positive because 1 over 4,200 is pretty small. So positive, positive, that means we are positive in there, which means n is increasing. Over here to the left of 0, if n is negative, well, n is negative, so that part's negative. And n being negative means this part's positive. So a positive times a negative is going to be negative. Not super surprising, because if you multiply this out, it would just be a parabola and it would be downward opening. So to answer question A, for what values of n is the population increasing? Well, whenever we're between 0 and 4,200. So I would say that n of t is increasing when n is between 0 and 4,200. And I would not include the endpoints here, because if n is equal to 4,200, the population, well, the derivative is 0, which means the population isn't increasing or decreasing. That would be my answer. And then there's a part B. Okay. So for what values of n is the population decreasing? Interesting question. I am kind of curious what you said his solution. Oh my gosh, I can't. No. Yeah, okay, fine. I'm curious what he said. So here's the answer that I think is correct. So when is the population decreasing? I would say specifically when n is bigger than 4,200. And that is my entire complete answer as far as I'm concerned. I don't believe I should include n being less than 0 because that doesn't make sense. The population can't be negative. You're talking about a population of people or animals that are alive, right? There might be something where it might make sense, but contextually here, right? If they say the word population, you really are thinking like people or animals. So now again, his solutions might say something different. I can't seem to log into Canvas right now, or that's not true. I can log in, but I have to go log in the LastPass first, which is a pain in the ass. So I don't want to do that. But if anyone's looked at the solutions and it has something different to say, I'm happy to hear it. But I feel like this is correct.
Yeah, it just says 4,200 to infinity.
Great, awesome. So yeah, so I mean, yes, maybe it might be better to write these as intervals. You could say 0 to 4,200 for this first one. You could say is 4,200 to infinity for the second one. Probably a technically better answer. And then part C, we've already answered. What are the equilibrium solutions? 0 and 4,200. Not surprising, right? That the equilibria are where you change from being increasing to decreasing or decreasing to increasing, right? That's not news to us, I don't think. All right. Moving on to number 13. Yeah, that's a good question. I might actually change it up a little bit. We'll see here. Oh, there's like 4 parts. Cool. All right. So 13. 13 says the following. Let R be the region enclosed by the graphs of y equal to x squared plus 1 and y equal to 3 minus x. Set up a definite integral that represents the area of the region. So part A, definite integral representing the area. And I'll say for the area, you probably don't need to draw the picture. But it's going to be useful to draw the picture for the volume part. I'm not going to draw it right now though, because I want to show you how to do it without drawing the region. So the very general idea here is that the area is going to equal the integral from some a to some b of the top function minus the bottom function, dx. To find the a and the b, right, the limits of integration, we have to set the functions equal to each other and find where they intersect. So we're going to set x squared plus 1 equal to 3 minus x. We're going to bring everything to the left. X squared plus x minus 2 equals 0. As long as the person has thought about the problem, it's usually a pretty good bet that this is going to factor. This definitely factors as x plus 2 times x minus 1. So my values are going to be x equal to -2 and x equal to +1. So -2 is going to be my a, +1 is going to be my b. And then very easily, we can figure out which function's on top by just picking some value between those 2 points. I would pick 0. You could pick -1 if you want, but I would pick 0 and plug it into both functions. So if you plug in 0 here, you get y equal to +1. Plug in 0 here, you get y equal to +3. Which one's bigger? Clearly 3. So that means this function is on top between, at least this function is on top for values of x between -2 and +1. So our area here is going to be the integral from -2 to +1 of the top function, not x squared plus 1, 3 minus x, that's the top function, as I just said, minus the bottom function, which is x squared plus 1. There's no reason to simplify this. Absolutely none. Because the problem says set up a definite integral. Does not say to solve it. And I think simplifying this if like, I would circle this as my final answer because this makes it really, really clear that you're saying, oh yeah, that's the top function, that's the bottom function. Whereas if you simplify it, it's less clear that you've done that. I think it's good to leave it this. I think it's better to leave it unsimplified than to do anything else. If you're just setting up. Okay. But now for these volume questions, which have us revolve around all sorts of different lines, I do think it's worth drawing the picture. Not just worth, I think it is almost necessary. I find it necessary anyway. So I'm going to draw the region. Luckily, I kind of know what these things look like. I know that x squared plus 1 is my usual upward opening parabola, except I'm shifting it up by 1. I didn't give myself a lot of room on the left here. Oh, well. So here's my y equal to x squared plus 1. And then the line y equals 3 minus x. Well, I know that these are going to intersect when x is 1. If x is 1, the y value is going to be 1 plus 1, which is 2. And if x is negative 2, the y value is going to be 3 minus 2, which is positive 5. Again, it doesn't have to be perfect. I'm just trying to get a decent idea of what this graph looks like. And I really kind of did not draw this in the best spot, which is stupid of me, but oh well. So there's my region. Green pen, please. And the first question for part B says, we want to revolve this around the line y equal to 1. This is part B, part 2. Part 2? I would start with 2. Oh, sorry, I missed the 1, sorry. The part 1 is around the x-axis. Sorry about that. The part 1 is x-axis. Okay, so for revolving around the x-axis, I feel like I'm very weirdly askew here. I'm going to draw what kind of strip? A vertical strip, because it's got to be perpendicular to my axis of rotation. So why do I keep losing the pen? There we go. Here's my vertical strip. And I'm just thinking of this distance, my outer radius, and this distance as my inner radius. Notably, whatever we do here, it's going to be the washer method, because none of my horizontal axes or my vertical axes could be the boundary of this region, right? This region is never going to be flush with a vertical axis or a horizontal axis. And those are the only kind of, right? No one's going to ask you to revolve this around the line y equals 3 minus x. So like always going to be washer method for this particular example. So here around the x-axis, the volume is going to be pi times the integral from still negative 2 to positive 1. That's not really going to change unless we do it in terms of y. My big radius squared minus my little radius squared, which in this case is going to be pi times the integral from negative 2 to 1. My big radius is the red function, which is 3 minus x. I'm going to say it slightly differently. My big radius is 3 minus x minus 0. It's the difference between the function and the axis of rotation. Oh, no, yeah. Sorry. I thought I said, sorry. My axis of rotation is y equals 0. This red function is y equals 3 minus x. This blue function is y equals x squared plus 1. And my large radius is the difference between 3 minus x and 0, which is just 3 minus x. But it's helpful to think about it in that context for the other ones. My large radius is 3 minus x, and we're squaring that. My small radius is the closer function, which is x squared plus 1 minus 0, which is just x squared plus 1. There's no reason to simplify this. Leave it like that. Don't do anything else. Okay, let's go to number 2. Number 2 now is a lot around the line y equals 1. And I'd really not like to draw this picture again. So let's see if I can get away with not drawing it again. So if we're going around the line here, y equals 1. Well, now my inner radius is a lot smaller. And my outer radius is also smaller. So it looks like my outer radius, well, again, it's the difference. And I don't love the way that looks there, sorry. Right, my outer radius is the distance from my further away function to my axis of rotation. So now my outer radius is going to be the further away function minus the axis axis of rotation. 3 minus x minus 1. And my radius got smaller. Instead of being all of 3 minus x, it's now 1 less than all of 3 minus x. And my inner radius is now just x squared. Well, I'm going to say it this way. It's x squared plus 1 minus 1. Once again, always really the distance from your function to the axis of rotation. And the distance between two things is always the difference between those two things. So we subtract. So here we're going to get that the volume around the axis y equals 1 is going to be still pi, still the integral from -2 to 1, still my large radius squared, 3 minus x minus 1 squared, minus my little radius squared, x squared plus 1 minus 1 squared. Yes, you could simplify the, oh geez, I'm sorry, it's so crooked there, apologies. You could simplify each of these, right? You could write this inside part here as just 2 minus x if you wanted to, and this inside part is just x squared. I don't particularly like doing that, even though it's a pain in the butt to kind of write it out this way, because I like to show that, oh yeah, it really is the difference between my function and my axis of rotation. I think it's nice to see that. I feel like I saw a hand, but maybe not. Okay. All right, and then we're going to go around the line y equals 5. So y equals 5 is actually right up here. So now if I look at the same strip, my inner radius is now this difference, and my outer radius is now that difference. We do want to do top minus bottom. So my outer radius is y equals 5. I should label that. My outer radius is y equals 5 minus my further away function, which is x squared plus 1. And my inner radius is y equals 5 minus my closer function, which is 3 minus x. This is especially why drawing the regions is important if you have these other axes of rotation. So you can really just look and see which function is the closer one, which function is the further away one. And it really does depend on where the axis of rotation is. So then for this one, the volume is going to be, once again, pi times the integral from -2 to 1 of your larger radius squared minus your smaller radius squared. Again, I don't think it's particularly good to simplify these, but if you wanted to, you could certainly write this as 4 minus x squared quantity squared, and this one as 2 plus x quantity squared. But I don't think you need to do that unless he specifically says you need to do that.
Why is there 5 in front of the function instead of being subtracted from it?
So the reason here is so, okay. Technically, you could subtract them in either order and it'd be fine because you're squaring. But I know the Dell likes people to do it the right way, and I feel like he would want you to make sure you subtracted the bigger thing minus the smaller thing so that our radius is positive. So if you look here, right, this function y equals 3 minus x between -2 and 1, the biggest it could ever be is 5 over here. But like in between, it definitely has values that are less than 5. So since this function is less than 5 almost all the time, we have to do the bigger thing, which is y equal to 5 minus the smaller thing so that the radius is positive. Like for example, if x is 0, the radius is going to be 5 minus 3, which is 2. If we subtract them the other way, the radius would be 3 minus 5, which is -2. Which again, technically doesn't come out wrong. But we almost always want to subtract the bigger thing minus the smaller thing. So that's why I like drawing the picture, because I can just look at the picture and say like, oh, look, for y equals 5, the axis of rotation is above the whole region, meaning I have to do the axis minus the functions instead of like here, y equals 1 was below, we did the functions minus the axis. But that's really why. It's just whichever one's bigger in value. And we're going to see the same thing here in a second when we do it around the other two axes.
So if you did it around like a negative number, like y is -2.
So I'm gonna say no, but technically yes. If it was around y, so actually let's just do it and we'll see what I mean. So if we did around y equals -2, what you would get would be Well, again, just like when we did for the one below here, right? We did our function -1 and our function -1. So I'm gonna do the same thing. I'm gonna do pi times the integral from -2 to 1. I can see that the red 3 minus x is the further away function from my made up y equals -2 down here. So it's gonna be the top function minus the bottom function, or I should say the top function minus the axis of rotation. So it's gonna be 3 minus x minus -2 squared. But minus -2 is really adding 2. So I really want you to think of it as subtracting. And then yes, when you subtract the negative number, it turns into addition. But think of it as subtraction first. And then the other part would be minus the inner radius squared, and the inner radius would be x squared plus 1 minus -2 quantity squared. So that's how I would definitely recommend you do it. All right, let's look at the other two parts of this, which are going around vertical axes. So let's draw the region again. Let's give ourselves a little bit more room here to work with. So here's my lovely parabola. Oh, wow. Lovely, James. Let's try that again. Sorry. Not my best work there. Again. So there's my parabola. There's my line y equals 3 minus x. And now we're going around lines like what? -2 and +1. And as long as your line, well, in fact, I didn't even say that. Never mind. And -2 is first up to bat. So we're rotating again this region. Man, yeah, not my favorite. Around the line x equal to -2. So since our line is vertical, our strip has to be horizontal. And kind of grossly here, we have to use two different strips. Because right here, if you're below that, your strip has the right-hand function being the parabola. If you're above that, the strip has the right-hand function being the straight line. Which is kind of super annoying, but such is life. So we know we're going to be using a dy, which means we need to write our functions in terms of y. So the y equals 3 minus x is going to become y plus x equal to 3, or x equal to 3 minus y. So there's x as a function of y. And the y equals x squared plus 1 is going to be y minus 1 equal to x squared, x equal to plus or minus the square root of y minus 1. And we really do need the plus or minus because the right-hand side, x is going to equal the positive square root of y minus 1. The left-hand side, x is going to equal the negative square root of y plus 1. Sorry, y minus 1. Sorry about that. Okay, so let's go around the line x equal to -2. Two integrals. The bottom one, well, there's my outer radius. There's my inner radius. So the volume is going to be first the integral from, we'll worry about those limits of integration in a second. The outer radius is going to be my further away function, the positive square root of y minus 1, minus the axis of rotation. So square root of y minus 1 minus -2. I don't know why I have an extra parenthesis there, sorry. Squared. Minus my inner radius, which is the closer function, minus -2, which is the negative square root of y minus 1 minus -2 squared. Gross. And we're not even halfway done yet. So then our limits of integration, well, this strip could go as low as that bottom point of the parabola, which is x equal to 0, y equal to 1. So it's a y value of 1. And as high as this point here, we found this point of intersection before, it was x equal to 1. If you plug in 1 for x, you get y equal to 2, or you get y equal to 2. The first half of this volume is going to be the integral from 1 to 2 of this outer radius squared minus this inner radius squared. Plus, the second half is now going to be this strip here. So now, here's my inner radius. There's my outer radius. So it's going to be the integral from as low as 2 to as high as, we got to find this point over here as well. When x is -2, y is going to be 4 plus 1, which is 5. And then same deal. The outer radius is going to be your further away function, which is 3 minus y, minus your axis of rotation squared. And your inner radius is going to be your closer function, which is the same as it was before. Negative square root of y minus 1 minus your -2 squared. And this is the setup for the volume of this region rotated around the line x equals -2. The only difference for the next part going around x equal to +1 is that instead of your function minus -2, it's going to be 1 minus your function to get the radius. But the outer and the inner are going to switch roles. And because now the further away function is the left-hand thing, not the right-hand thing. So, oh, it's 10:22, sorry. So you can leave if you need to. Let me just wrap this one up though real quick here. Oh, and yeah, good question. What did I forget? Yeah, don't forget the tastiness. You need the pie. So then to answer the very last part of this very long question, we would go around this axis here. So the volume would be, so for the bottom half, it's going to be pi times the integral from a low of 1 to a high of 2. And now my outer radius is going to be the difference between my axis of rotation and the further away function. So it's going to be 1 minus the further away function, which is the negative square root of y minus 1 quantity squared, minus the inner radius, which is 1 minus the closer function, which is 1 minus the positive square root of y minus 1 quantity squared. Plus the upper part of it, which is going to be pi times the integral from 2 to 5. And now my outer radius is going to be 1 minus the further away function, which is still the same as it was before. 1 minus the negative square root of y minus 1 squared, minus the inner radius, which is now going to be 1 minus the closer function, which is 1 minus the closer function, which is 3 minus y quantity squared dy. Yeah. So I can't imagine someone would ask, I really can't imagine someone would ask you to do all 5 of those on. That's kind of a lot. But I can certainly see asking 1 or 2 of them. Like to set up an integral for the revolution around an axis that's not the x-axis or the y-axis. I feel like that's fairly likely that you'd be asked to set up an integral where you're revolving around a different axis. All right, I should definitely stop talking because it's 10:24. I have office hours as usual. And for those of you taking an exam tomorrow, good luck. I hope it goes well. And for those of you